This video is going to be the first of 3 videos on looking at solving equations to do with roots of polynomials, where we're given an equation and we're told we have roots alpha, beta, and gamma in the case of a cubic, or in the case of a quadratic, alpha and beta, or you might even have a quartic with 4 roots, and we'll be asked to find equations with roots related to those original roots. Now, the reason we're going to have 3 parts on this is because you've got 2 different methods you can use. You can either use a substitution, or there's going to be cases where there's no natural substitution to make, and we'll have to use roots to do with either the product of the roots, or the sums of the roots, or even the sums of the product pairs, but that will come in the next part. The third video is going to go back to looking at substitution, but in less obvious cases where you can save yourself a lot of algebra if you can spot a clever way in. But this one's probably the most standard setting to get us into this. So we're given a cubic equation here, we're told it has roots alpha, beta, and gamma, and we're asked to find an equation with roots 2 alpha minus 1, 2 beta minus 1, and 2 gamma minus 1. Note, we want to do this without needing to find alpha, beta, and gamma because those roots aren't going to be nice for us to work with. In a case like this, we're going to start by saying, well, the reason we can make a nice substitution here is because each of these 3 new roots is doing the same thing to our old roots. We're taking our old roots, we're multiplying by 2 and subtracting 1. And that tells us straight away we want to make the substitution of w equals 2 times z subtract 1 because we're taking our old values, multiplying by 2 and subtracting 1. We're then going to rearrange to get z equals, so add 1 to both sides. Sorry, something went wrong with my pen there. We're going to say that z is equal to w plus 1 over 2, so adding 1 to both sides and dividing by 2, and substitute this in to our original equation. So we'll end up with 2 brackets w plus 1 over 2 all cubed, plus 3 brackets w plus 1 over 2 all squared, subtract 6 brackets w plus 1 over 2, and then plus 7 equals 0, just from going back to our original equation and replacing all our z with w plus 1 over 2. At this stage, it might be tempting to expand straight away. I would recommend you hold off because we've got a lot of fractions to work with. Let's deal with those fractions first before we have a lot of algebra going around everywhere else. So if we were to deal with this fraction and write as the first fraction, deal with right as 2 separate parts, we can have w plus 1 all cubed over 2 cubed, or w plus 1 cubed over 8, and then we're multiplying by 2. So this first bit is just going to become w plus 1 cubed over 4. Similarly, this next bit will be 3 lots of w plus 1 squared over 2 squared, or over 4 again. We've then got 6 over 2, which is 3. We just need to be careful here that you don't just write this and ignore the brackets. We're subtracting 3 lots of w plus 1, so keep the brackets there, and then plus 7 equals 0. At this stage, again, hold off expanding and get rid of these fractions first, because these fractions are only going to make our life more difficult, and we're asked in the original question to get an equation with integer coefficients, so we know we don't want fractions at the end anyway. So what can we do? We can multiply each term by 4. That's going to make life a lot easier for us, so we'll get w plus 1 all cubed, plus 3 lots of w plus 1 all squared, subtract 12 lots of w plus 1, again make sure you keep those brackets, and then plus 28, and 0 times 4 is just 0, so that's all fine, we've still got an equal 0 there. Now we do need to expand. You want to use your knowledge of binomial expansions at this point. You don't want to have to be writing w plus 1 times w plus 1 times w plus 1. You could, but it's more likely there's a mistake going to creep in there. So when we expand this, we'll get w cubed plus 3 choose 1, or just 3, w squared, and then plus 3w plus 1. This next one, well, w plus 1 all squared, you should be able to stay that by now, is w squared plus 2w plus 1. So if you times that by 3, you'll get plus 3w squared plus 6w plus 3. Then being careful here, we go minus 12w minus 12 plus 28 equals 0. Let's now simplify this down. So we've just got 1w cubed. We've got 3w squared and another 3w squared, so 6w squared. We then got plus 3w plus 6w minus 12w, which is going to give us subtract 3w. And finally, plus 1 plus 3 subtract 12 plus 28 is going to give us plus 20 equals 0. So this is our final equation. You need to make sure you state that equals 0. You're asked for an equation. If you don't write equals 0, you will lose a mark on an exam because you're just writing an expression there. So whenever you have a situation where you're doing the same thing to alpha, beta, and gamma, and it's a nice linear transformation, you should be able to make a substitution like this and work it through. Now, there's going to be some cases where we can do a substitution despite that. I want to look at one slightly more complex case here, although like I say in the third video I'll make on roots of polynomials, we'll look at even more complicated cases. The situation I want to look at here is I want to say, let's consider just a quadratic this time. Let's imagine we've got the equation 2z squared, subtract 8z plus 9 equals 0. We'll say that has roots just alpha and beta. No gamma this time because we've only got 2 roots. And we want to find an equation with roots alpha squared subtract 1 and beta squared subtract 1. Now you should be cautious seeing this here because this isn't a linear transformation anymore. We've got to square them. We are doing the same thing to alpha and beta, so there's going to be a natural substitution to make, but we could get in trouble. We'll go through it, we'll see why it does work in this case, and then we'll be able to see how we might be able to predict when it will and when it will get us into trouble. So let's make a substitution here. Let's make our substitution W is equal to z squared subtract 1 and rearrange that. So we're going to z squared equals w plus 1 and square rooting. I'm not going to worry about the plus or minus. We'll see why we don't need to worry about that in just a minute. So at this stage, let's sub in and let's see what we get. And as I say, we'll see why I'm being a bit careless about this plus or minus square root here. So if we do substitute in here, we're going to get 2z squared. Well, that's just going to be 2 root w plus 1 all squared, so 2 of w plus 1, subtract 8 root w plus 1 plus 9 equals 0. This isn't going to be an acceptable form to leave your answer in. Admittedly, we have found an equation with these roots. It's likely in an exam we will explicitly say find a quadratic equation, but even if it doesn't, you can be pretty sure you won't get a marks for leaving your answer in this form. We don't want this square root here. Now, in this case, we can deal with that. If we get this square root isolated and then square it, we won't have a square root anymore. So let's expand the other bits we can first. So we're going to get 2w plus 2 plus 9 or plus 11, subtract 8 root w plus 1 equals 0. And then if we get the square root just onto a side by itself, now we can square both sides. We couldn't square before because we'd end up with lots more terms involved in square root. But having got it on a side by itself, if we now square both sides, so 2w plus 11 all squared, here we're going to get 8 squared or 64 times root w plus 1 squared, which is just going to be w plus 1. And we can expand 4w squared plus 44w plus 121 equals 64w plus 64. And now we just need to rearrange and we'll get 4w squared subtract 20w plus 57 equals 0. So firstly, why didn't I have to worry about the plus or minus? Well, if I'd gone for the negative square root here, we squared it to get this w plus 1, so the negative would have disappeared there anyway. And at this point, we squared this and the negative would have disappeared there as well. Now, does that mean you can always make a substitution? If I'd wanted alpha cubed subtract 1 and beta cubed subtract 1, we'd have ended up with a cube root here, and this would have had a cube root involved, and this would have had a cube root involved, and you'd have really struggled to isolate those. It might have been possible after multiple steps, but it's not going to be the nicest way in those cases. So in the next video, we'll look at what to do if you don't have a nice substitution to make. But because we were going to have only a quadratic, we couldn't get away with making a substitution. Again, if this had been a cubic equation with a z cubed in there and you were making this substitution, you'd have ended up with 2 lots of the square roots. And again, you might have found yourself getting into trouble. I'm not saying it's impossible, but I'm saying it would be making your life harder than what's going to come in the next video. So we'll look at that then. But hopefully you found that useful. And if you want to see how to do situations where you can't make a square root, look for the next video in this series. Thank you very much.